Let's jump right into this explainer. We're going to demystify the black box of artificial intelligence and look at how deep learning is actually transitioning from this sort of trial and error alchemy into a rigorous, highly predictable science. If you've been following the massive leaps in AI lately, you already know the models are getting larger, way more capable, and infinitely more complex. But right beneath the surface of all that rapid progress, there's a profound scientific shift happening, and that's exactly what we're unpacking today. Which brings us to a fundamental question. Will we ever truly understand how AI works? Today's neural networks are routinely hitting superhuman performance on incredibly complex tasks. Yet historically, they've been totally inscrutable systems. We build them, sure, but we don't fully grasp their internal workings. It leaves researchers wondering if we'll ever actually decipher the underlying laws governing them. I mean, are they just massive chaotic matrices of numbers? Or is there a hidden order in there just waiting to be discovered? Well, here's our roadmap to find out. We're going to look inside the black box, meet this concept of learning mechanics, see how we can simplify complex systems, discover empirical laws, check out universal behaviors in AI, and finally, discuss exactly why learning mechanics matters. So, part 1, Inside the Black Box, the mystery of superhuman AI. We've got to start by acknowledging this really fascinating empirical tension. In a literal sense, modern neural networks are completely transparent. We write the code, we set the parameters, we feed them the training data. Literally nothing is hidden from us. And yet, when all those components actually interact, they create these nonlinear, high-dimensional learning dynamics that are just wildly unpredictable. But, as researchers are boldly pointing out right now, a true scientific theory is emerging to explain all that chaos. Specifically, they're calling it a mechanics of the learning process. We're finally moving from just observing what a network does to establishing an actual, rigorous mechanics that dictates exactly why it learns the way it does. Part 2, Meet Learning Mechanics, from alchemy to physics. To really get where we are in AI right now, it helps to look back at history. Think about it. Early engineers built steam engines way before anyone actually understood the laws of thermodynamics, right? Well, we've essentially built AI without understanding its foundational physics. The conceptual anchor here is brilliant. Classical physical mechanics studies how forces move objects through physical space. Learning mechanics maps to that perfectly, except it studies how gradients move mathematical models through parameter space. So the interactions between your data, your architecture, and the task itself, they generate these gradients, and those act as the forces steering the model toward an equilibrium. Now, to be considered a true science, this new framework has to meet some seriously rigorous standards. It can't just be high-level philosophy. It has to be fundamental, mathematical, predictive, comprehensive, intuitive, useful, and humble. It has to move from qualitative guesswork to a hard mathematical framework that makes unambiguous, verifiable predictions about how a network trains and represents data. It needs to be incredibly useful for engineers, comprehensive enough to connect raw data to the final weights, but importantly, humble enough to know exactly where its predictive power breaks down. Part 3, Simplifying Complex Systems, Linearization and Limits. So how on earth do you study a system that has hundreds of billions of interacting parameters? Well, you simplify it. What's really cool here is that when you simplify the math by linearizing the data or the parameters, the exact theoretical predictions perfectly map onto the real-world experimental dots. Even with incredibly complex concepts like neural tangent kernels, which are basically mathematical shortcuts used to understand infinitely wide networks, they prove that the underlying dynamics of gradient descent can actually be exactly mapped and mathematically predicted. And that leads theorists to lean heavily on mathematical limits. The big idea here is the discretization hypothesis. It basically states that practical, everyday neural networks can be understood as noisy, finite approximations of theoretical models pushed to an infinite size. It sounds crazy, but by mathematically pushing network width or depth to infinity, this immensely complex system actually simplifies. It strips away the noise and reveals foundational macroscopic behaviors that hold totally true even when you scale things back down to finite practical reality. A perfect concrete example of this is the lazy versus rich dichotomy. If you don't scale the initialization correctly as a network gets infinitely wide, you trigger what's called lazy dynamics. It learns, sure, but its hidden representations barely change from initialization. It's basically phoning it in. But if you scale it correctly by lowering the output multiplier, you force that network into a rich regime. Suddenly, it's actively adapting and learning highly complex internal features, which is exactly what we need our deep learning models doing. Part 4, Discovering Empirical Laws. The macro statistics of AI. Okay, if learning mechanics is going to be like physics, we need laws. Think of Kepler observing the planets before gravity was fully understood. Well, neural scaling laws are an absolute wow moment in this field. Despite an AI model having literally billions of interconnected parameters, its test loss, basically how well it performs, drops in a perfectly predictable, straight power law line based on just 3 simple variables: the amount of compute, the size of the dataset, and the number of parameters. You honestly don't need to track every single neuron to accurately predict exactly how smart the network is going to get.
And we're even seeing these empirical laws in the loss landscape itself. During training, the sharpness of the network loss doesn't just bounce around randomly. It predictably rises and plateaus right at what theorists call the edge of stability. Mathematically, that's defined as exactly 2 divided by the learning rate. Any sharper than that, and the training breaks, it becomes violently unstable. But the network naturally finds this precise, razor-thin edge and just rides it all the way down.
These kinds of discoveries are driving incredible engineering efficiencies. By using frameworks like maximal update parameterization, or MUP, we can effectively disentangle a model's architecture from its optimization hyperparameters. This means theorists can perfectly tune learning rates on tiny, ultra-cheap models and then seamlessly transfer those exact rates up to massive, super expensive models. The optimal learning rate stays incredibly stable regardless of how wide the model gets, which obviously saves an absolute ton of compute and prevents endless trial and error. Part 5. Universal Behaviors in AI, Shared Phenomena Across Models. If the true physics of AI actually exists, it should apply everywhere, right? Just like fluid dynamics applies equally to water and air. And that's exactly what we are seeing. Entirely different AI architectures, like UNets and vision transformers, when tasked with generating images, end up converging to the exact same learned distributions. If you feed them the exact same initial random noise seed, these completely distinct architectures will spit out virtually identical images. They're independently learning universal inductive biases about what our visual world actually looks like. It's mind-blowing.
And this universality even crosses completely different data modalities. Remarkably, as massive language models get better and better at processing text, their internal mathematical representations actually start to align with those of pure vision models. Think about the implication there. Whether an AI is looking at pixels or reading text, as it gets smarter, it begins to form a universal, shared mathematical representation of reality.
Part 6. Why Learning Mechanics Matters: The Future of AI Science. So, why does transitioning from this sort of AI alchemy to strict mathematical mechanics actually matter for the future? Well, it matters for 3 massive reasons. First, scientifically, it explains the fundamental principles of intelligence itself, abstracting it completely away from biology. Second, on a practical level, it replaces wildly expensive guesswork with reliable, predictable engineering. And third, absolutely crucially for safety, it provides the rigorous mathematical foundations we desperately need for AI alignment and mechanistic interpretability, so we can actually control these powerful systems before they are deployed. We are standing in the middle of an incredible paradigm shift, which leaves us with one final, really profound question to ponder. If we can actually distill the high-dimensional chaos of artificial neural networks into predictable, universal laws of physics, what hidden fundamental laws might we soon discover about the workings of our own biological minds? Because if intelligence ultimately boils down to a mathematical mechanic, then understanding the physics of AI might just be the absolute key to finally understanding ourselves.